Last time we did areas just with one graph. Today we're going to have two graphs. And so you all do have your computers because I want you to be able to practice typing these in. But if I can tell they're distracting you, you'll have to put them away and then you'll just have to watch me type, which won't be as fun. Okay, I want you to practice typing them as well. So what we're going to do, I'm going to share my screen. We're going to type both of these in so that we can take a peek at what the graph looks like. So everybody just go ahead and take a minute and type them in. I got this. What did you get? And we'll take a look at the graph. I literally just started the lesson part. Your paper that you see.
They're both the same.
They're both the same.
Yeah, that's what I said.
This circle is the same as that circle.
Yeah.
Right, but I am recording, so let's.
Sorry.
No, you're fine. Whoever's listening to the recording will be like, "Oh, that's interesting."
Circles are awesome.
Circles are awesome.
Oh, so now we're gonna have to find the side.
No, I should leave it cracked. Sorry.
I thought I left it open. No. Don't shut it all. Or yeah, just don't shut it at all. Everybody's going to be coming back.
So it's like a chart. Charts like two circles in a second. What chart? It's not like gravity.
All right, so all we did is type both of these in, and I'm just giving everybody a chance to get settled because half the class just came back. So you should have one that's a circle. That's mine. That's red. Yours won't be the same colors necessarily, but and then what do we call the blue one? Do you remember that? It's a cardioid because it looks like heart. So the directions say we want to find the area. What does it say? Common to both of them. So watch where I have my cursor. That means that we want the part that is in here. Do you see where my cursor is going? Okay. So we're going to do what I'm going to call them the red graph and the blue graph. On your computer, they're probably two different colors, but I have to, explain it the way I have it up here. We're going to go from here to here, this intersection, for the red graph. And then we're going to go from here to here for the blue graph. Do you see where I was pointing at? Okay, from there to there for the red one, from there to there with the blue one, that will give us all of this area. And then we can just multiply it by 2 to get the whole thing. Are we on board with what we want to do? Okay, because I'm going to go back and I'm going to set it up. You guys know me by this point. I'm a big fan of set it up blank, and then we can just go back and fill in the parts that we don't know. I feel like it calms me down. I'm like, okay, I started. Okay? So it's going to be 1/2 integral something to something of the, mine was the red one. It was the circle one, right? Yeah. Yes, we want to do the circle first. All right. So -6 cosine theta squared d theta plus, and then I'm not going to say it all. That's annoying to listen to me just like verbalize all of that. But I set it up as my formula. And then we want to take that entire thing and multiply it by 2. So what I would do is just not type the 1/2. And does that answer the question that conversation we were having earlier? Yeah. Because if you distribute this 2 through here, distribute it to both of those, the 2 and the 1/2 are just going to cancel if you distribute it through. So I just wouldn't bother typing them. That is me. All right. So I'm going to go back to my graph so that I can use actually, before I go back to my graph, one of the boundaries that we need is the intersection between them. And so what I'm going to do is set them equal. So let's start by setting them equal to each other because we are going to need that intersection. So set them equal, and then we're going to do a little bit of algebra and pre-calc. I'm always used to calling it pre-calc. You guys know why you call it math analysis here? I've never heard that before.
I don't know.
Pre-calc is what it is. Or trigonometry.
We didn't even do trigonometry.
So what we would do to both sides, to get rid of the -2 cosine, we would do +2 cosine. So if you add this over, -6 cosine plus 2 cosine is -4 cosine. And then you would divide by -4, that's -1/2, which is on the unit circle. Go figure. Cosine is your x value. That's going to be negative in quadrants 2 and 3. So think about it. We want something in quadrant 2 and quadrant 3. If I give you the first one, It's 2 pi over 3 and 4 pi over 3. 2 divided by negative 4. I just divided the negative 4 over. All right, so I'm going to share my screen again. We're going to go back to our graph. The hardest part of these polar areas is figuring out what your boundaries are, okay? And you're especially not going to like this one, because where does it look like we're going to start? But it's not. All right, if you plug 0 into this equation, this one that I'm pointing at right here, what is cosine of 0? 1 times negative 6. So it actually starts right here for 0. All right. This one is going to be pi over 2. If you plug in pi over 2, what is cosine of pi over 2? 0. So that's what puts you there. So this circle's rotation starts right here and then goes around. So our first boundary is going to be pi over 2. And then the next one is the intersection. What's the first value we got from that little equation that we just saw? 2 pi over 3. Okay. I'm going to have to just share and unshare again because I can't talk us the whole way through it. So we're going to go from pi over 2 to that intersection, 2 pi over 3. And then this one is going to pick up where that one left off. So it's going to be 2 pi over 3 to whatever. And I'm going to have to share again to get back to my graph. Sorry, I know it's a lot of button clicking. We're going to get through it together. It'll be okay. I want to end right here. Do you see where my cursor is? On the blue graph? So that would be what? So that is the distance from the origin. But I want the amount of rotation, like the theta, that will get us there. This one's 2 pi over 3. So this would be pi. Okay? What would this intersection be? We're not going to need it, but we found it. That one is 4 pi over 3. Okay, good. We're not going to need it, but that is what that would be. All right, so this is pi. Everybody practice typing it in. We're all going to make sure we got the same thing.
So we would just type in 2 and times all that.
I wouldn't even do the 2 because the 2 and the 1/2, like if you distribute a 2 through here, they're going to cancel. So I wouldn't even type the 2's at all, but that's a personal preference. I know. I'm going to do a lot of pep talking for you here. In my opinion, I think the hardest part of this entire problem was the fact that that first lower boundary wasn't 0. In my opinion, I think that was the hardest thing, is that it wasn't 0, it was pi over 2. Yeah, I'm not even there yet.
What did you get?
Getting there.
Yeah, I was going to say. Okay, I got that same thing. I would truncate on the AP exam, but when you go to do your delta math, it does round. So it would be 15.708. And if you're not there yet, just still take your time. I'm just going to write it down so that we have the answer up here. To find, yes, the intersection for that boundary. And this is the intersection that was like on the lower part. We just didn't end up needing it, but that's what that intersection was going to be.
Would you be able to use the intersection at the bottom?
So instead, it would be way more complicated. Instead of just 2 integrals, then you'd have to like go further and have another one. Like, just trust me that I'm always going to show you what I think is the easiest way to do it. With polar, there's a lot of options though.
We use pi because like with the last thing that's where equal to 0.
Correct. Yeah, or think of like pi is over here on your unit circle. Like that's where that rotated to. All right, can we move on to the next one? Okay. This just says write an integral, so we don't have to actually work it out. We're just going to set it up. Area bounded by this and the line y equals 2x in the first quadrant. All right, so let's go ahead and type it in just so that we can get a visual of it. Because it is just nice to have, you know, an idea of what it is you're actually finding. Because also, does everybody understand if you got a negative answer, that's wrong? Like we're finding an area. You get that, right? Or like if you got an area of 6,000 and something, that's not going to be right. I'm just making sure that you could go, oh, whoops, I must have typed something wrong. Now, I should have been a little bit more specific in my directions with this one because there's actually 2 sections that it could be talking about in the first quadrant. We're going to do this one. Do you see where my cursor is? All right, we're going to do that one. So we want to go from 0 until whatever that is. You're not going to like it, okay? But we want to go from 0 until whatever that intersection is of this rose graph, okay? So let's go ahead and set it up. We have practically everything that we need. It's going to be 1/2 integral starting at 0 pi, and then this squared d theta. So we have practically all of the ingredients, right? The only thing we're missing is that upper boundary, and it's not on the unit circle, okay? And the second thing that's not cool is this is in polar, but this is in, what do we call it? Begins with an R, rectangular, okay? So we have to take what I taught you way back in the beginning of the polar. I say way back in the beginning. It was only 3 classes ago, but that does feel like a lifetime. Tangent of theta equals y over x. It's this right here that we were talking about before. Tangent is opposite over adjacent. That ends up being y over x, okay? So what is y equal to? 2x. So tangent of theta equals 2x over x. And so tangent of theta equals 2. And how do you undo a tangent? Like how do you undo, because we want, yeah, and what do we call that though? It's tangent, it's arc tangent, but it's tangent inverse. Who said inverse? Inverse. All right. But it is tangent inverse of 2, whatever that is. You're welcome to type it into Desmos if you want. It's some kind of decimal, but that is what goes right here. Tangent inverse of 2. And that's it. You don't have to do anything. I guess you could type that in if you want, but it didn't say to do that, and I'm lazy, so I'm moving on. And you can write arctangent, because I know you said arctangent. It's just that's a little shorter. Yes, it's y over x, and this is what y equaled. Yeah, so whatever the equation was, say it was y equals 7x. Actually, we would have ended up with tangent inverse of 7. You know, it's just like whatever. It's the slope of the line. If you missed that little conversation. Anyway. All right, consider this polar curve, which is interesting. It is r of theta equals theta cosine theta. Oh, yeah, go ahead. Tangent inverse of 2. You okay? Okay, go ahead. Oh, are you getting the area? You can if you want to. All right, so for this one, here is our equation. You can put a box around that or circle around it. It says the derivative is given by this. We don't need that for the problem we're going to do. Do you see how it's just part A? I pulled this from a free response question, and you would have needed that for like parts B, C, D, but we're not going to do those, so you can get rid of that. We don't need that. And they gave us the graph right there. We want the area for the inner loop. So again, let's just set it up. That theta is not very good. I'm going to fix that. And again, the hardest part is the boundaries. That's what we need to find. So if you watch me point to this, I don't know if this polar graph goes around the inner loop first and then the outer one, or does it go around the outer one first and then the inner one? So that's really what we need to figure out in order to get our boundaries, okay? So what I would do is just start trying to plug in some numbers. And if you don't want to make a table, if you can hold them all in your mind, that's fine. I'm just going to write them out, and I'm going to start with 0, which I'm pretty sure is just going to be 0, right? Yeah, if you plug in 0 for theta, 0 times 1 is just going to be 0. So we are going to start here, But again, I don't know if it goes around the big loop first or the little loop. So let's hold off on putting any boundaries in it. I would do, let's see, what will be a good one? Let's do pi over 3. Cosine of pi over 3 is a half. And then times pi over 3. So a half times pi over 3 is pi over 6. So pi is about 3. So if you like estimate, this would be about 1/2, which is probably going to be like, do you see how this is 1 and this is 1? So 1/2 is going to be like right about there. Do you see what I'm saying? We're going to go around the inner loop first. So I can safely say to get the inner loop area, we're going to start at 0. And then I need to figure out when this goes to 0 again. So when is cosine going to equal 0? I need to know when I'm going to hit the pole again. Pi over 2 is going to give us 0. And then you're going to throw this in your calculator and get an answer. And it should be very, very, very teensy tiny because we want this tiny little loop. It's not a race. Okay. Yeah, is it very little? It should be. Oops.
1, 2, 7.
Very small number.
All right, so I would truncate, but again, delta math is going to round. So if you were typing this into delta math, it would be 0.127. Good job. I'm glad you're all enjoying the polar graphs. It is fun. Oh. You get out of school what you put into it, I suppose. All right, so this one gave us a picture too, which is good. It says, oh, geez, is that our graph? I guess that's not too horrible. 2 sine squared and 4 sine squared. We don't need to actually type it in the calculator. We just need to pick which one of these is the setup. We want which area because there's kind of 2 things going on here. We want the region bounded by, oh, well, I'm not even there yet. We want the part that is between. So the area we want is that. Okay. So you can do 2 different integrals if you want, but if they start and end at the same place, you can actually get away with just making 1 integral. If they start and end at different places, you have to do 2 separate integrals. But do you see how these start and end at the same location? Okay. We can get away with just doing 1. And do you see how these are all only 1? All right. So 1/2 integral, it's going to be the bigger one squared minus the smaller one squared, d theta. Does that make sense? Because we want the part in between. Do you remember washer method? It's that, but for polar. So which one is the bigger one? Yeah, 4 sine squared. And then this one would be 2 sine squared. And then we just need to get the boundaries. So sine of 0 is 0. Actually, aren't all the boundaries on the choices the same? Oh, okay, cool. That was really nice of them. We didn't have to even worry about the boundaries because they were all the same. Now, first, we're going to square these things. So 4 squared is 16. So this is 16 sine squared. Oh, not sine squared at all. It would be sine to the 4th minus, and then 2 squared is 4. And I'm probably just going to talk you through the rest so we don't have to write anymore. You have to write enough, though. Like, it's hard to do it all in your head. So let's subtract. 16 minus 4 is 12, but we want half. So it's going to be 6 sine to the 4th. So which one says that? D, as in delicious. Well, I feel like you should have narrowed it down to either C or D. Why should it have been C or D? Yeah, there's that sine squared. We knew it should have been to the 4th. All right, this one I would like a picture of, so let's go and type that in our calculator. All right, how does this look? Oh, it's a little loop. Do you remember what these are called? These with an L? Nemeson. Yeah, with the little like accent on the C. All right, what does it want? That's the picture, but we want the area between the inner and outer loop. Okay, so watch where my cursor is. We want all of, it keeps disappearing. We want all of this. Everything except the inner loop. These don't start and stop at the same amounts of rotation, so we are going to have to do two separate integrals for that, okay? But we're going to do the whole big loop minus the small loop. Okay, let's just start at 0. If you plug in 0, because I don't know where the rotation starts. It might not start at the pole. Let's find out. Sine of 0, 0. So that would give you 1. So your rotation actually starts here. This is where 0 pi is. So where is this going to start? I would guess pi over 6, because sine of pi over 6 is a half. Sine of pi over 6 is a half. Times 2 is 1, and then 1 minus 1 is 0. Okay, so for the inner loop, it starts at pi over 6, and then it goes to, where is the other place where sine is going to be a half? We did the one in the first quadrant. In the second quadrant, so we have pi over 6. What's the one in the second quadrant? It's going to be something pi over 6. 5 pi over 6. Okay, that's enough. We can't hold so many numbers in our head. I'm going to get it set up, and we'll fill in what we know so far, and then we'll go back, because that's just too much, right? Oops, I forgot my 1/2. I can't hold that many numbers in my head. I'm going to have to go back. We found that for the inner loop, it was pi over 6 to 5 pi over 6. So you have two integrals that have like the same stuff inside, which is called the integrand, by the way. So the integrand is the same for both of them. They both have a 1/2. We're just going to change the boundaries. So we found for the inner loop, it was pi over 6 to 5 pi over 6. And I'm going to let that just marinate for a second, give everybody a chance to write it down, and then we'll go back and figure out the boundaries for the larger loop. And then we'll put it on the calculator and get an answer. It's more split evenly than other tests you've had before. Okay. And a bunch of the non-calculator ones are kind of like this, where you don't actually get an answer, you're just setting it up. Because it's very difficult to get an answer for these without a calculator. So yeah, there is more calculator than not. I'm getting there. I was just trying to pause a second and give everybody a chance. Are we all okay now? I didn't want to try and rush everybody. All right, so let me point to this again. So follow my cursor here. Let me get this out of the way. So we said this inner loop was pi over 6 to 5 pi over 6. So when I go to do the outer loop, it's going to start at 5 pi over 6, and we need to figure out where it ends. So your lower boundary is going to be 5 pi over 6. Now come with me. Where did we start here? Because it wasn't at the pole. We talked about that. We started at 1. So that's 2 pi. That's the whole way around. We need to go another 6 further to close it. So let's talk our way through that. 2 whole pi, the whole way around, is how many 6? It's 12 6. And then if you have to go one more 6 to get back here, good job, guys. 13 pi over 6 is that upper boundary. While you're typing that in, and I want you to practice doing it. I know it's not fun, but that's kind of why we need to practice it, okay? So we can work out all the kinks now. My pep talk for this is, if you got this on a free response, if you were able to figure out all of it except for the boundaries, you would still get probably 2 points out of it. Do you get what I'm saying? So like throw whatever you know at it if you do the setup and then just can't get these, you will still get something. It isn't going to be a total wash, okay? So I know it seems overwhelming and it's a lot, so I do a lot of pep talking. I think you can get some of the points. And remember, if the problem is worth 4 points and you get 2 out of it, isn't that half and that's good? Yes. Shoot. All right, well, me taking this phone call is going to be in this recording because I can't pause it again. This is my school. Yeah, what room? Okay. Okay, thanks. Can you guys go to 2022? Is who?
Oh boy.
Is that a good thing?
Oh, no.
What did you all get for this? Does it look like about 8, or does that seem like that makes sense to you? I know this goes down to 3, so I'm almost there. Oops.
I also have this.
8 point.
Oh, I didn't understand the question.
Oops.
Wait, no, but that's
Point though.
Cool. So how would we round it? If you round it wrong, Delta Math is going to mark it wrong. It's 8.338. Good job. 8.338. All right, one more. I actually copied this one from Delta Math, so I could do one exactly like what it's going to look for you. I tried to make the other ones sort of mimic them too. All right, so let R be the region inside both of these curves. We have 2 sine squared and 5 cosine squared. First, let's figure out which one is which, okay? Sine of 0 is 0. That's going to start at the pole. Let's do pi over 2. What is sine of pi over 2 up at the top there? 1 squared is 1 times 2 is 2. That's going to be right here. So the snowman looking one, or the one kind of like the infinity, that's the 2 sine squared. And then this other one, which they just didn't finish it. It's going to be like this. Do you see what I'm saying? Like, it's just off the grid. That's the 5 cosine squared. It would go out to 5. The grid just doesn't go far enough to go out to 5, right? So we're going to do 2 separate integrals, and we're going to cut it where they intersect. Do you understand what I'm saying? To get this little pedal, we're going to go from here to the intersection, and then from the intersection to here. So let's set it up. We're going to have 2 integrals added together. We just have to decide which equation goes in which one and then get our boundaries. That's the hardest part. Let me point to it. We're going to do this area first. That's the part that follows the 2 sine squared. So that goes there. And then the other half of the leaf is the one that follows, yeah, this one, the 5 cosine squared. That wasn't that bad. We figured out which one goes where. Now we need boundaries. So for sine, we start at... So do you see which one I'm tracing? Yeah, so that is the one that's this one. That's the sine squared one. And then the second half is this one. You have to throw that out the window. It's a rotation.
Oh.
Hold on. I want you to understand this. Let me draw it larger than this. You're not seeing it because I can't draw it any bigger. This is the pedal we're finding. Do you see that? It's not upper minus lower or right minus left because it's not rectangular. It's polar. We're rotating through it. So we rotate and gather area like this. Do you see? It's a rotation. You have to throw all of it's a completely different language, so to speak. It's not rectangular. Okay? So this one, the one that we're rotating through first, is the sine squared one. And then this one, the one we're rotating through second, is the cosine squared one. So we're going to start at 0 pi, and it's going to go to this intersection, which I don't know what that is yet, so just hold on. And then what's this lower boundary going to be? Well, whatever that is, once we find it. And then where do we stop? So we need to know where this 5 cosine squared graph gets back to 0. Cosine is 0 at what rotation? Pi over 2. So let me show you how we get the intersection. And it's kind of a cheat, but it's sort of easy because you don't even have to know the unit circle to get it. Let me share so this shows up on my recording. We are going to kind of pretend it's rectangular for a second to get this to tell us the answer. Go ahead and clear out everything you've got in your calculator. This is sort of like a trick, but all right. In the first one, we're going to don't put r equals 2 sine squared of x, and then we're going to put 5 cosine squared of x. Now, there's an awful lot of intersections here. Which one do we want? The first one, which is this one right here. So I got, well, here I'm going to export that point so I can copy and paste it, but I got 1.00685. Do you see that? That's the number that goes on those boundaries that we didn't have. So 1.00685. And now we're all going to have fun typing it in to get our area. That's the boundary that we were missing. That's that intersection. I just graphed the two equations. I did it in rectangular though, because if you do it in polar, Desmos won't click the intersection for you, which is like really a bummer. But if you put it into rectangular, if you put it with an X instead of a theta, it'll do it for you.
So
Let me copy and paste it.
did we find the bottom boundary for 2 sine squared?
It's the same number
Oh, intersection.
Oh.
because it's the intersection. So it's where one leaves off and the other picks
Yeah,
up.
oh, sorry, yeah, I just didn't have the bottom boundary.
Are you done already? It's not a race, and don't rush. 5, what was this one? Cosine squared. Another squared. All right, what did you get? Because I finally finished.
I got a weird number. I love that.
It should be a decimal.
Yeah. 0.377.
I also have something.
Now, if you put 0.377, it's going to mark it wrong. It should be 0.378. So, but to clarify, 0.377 is 100% perfect for the AP exam. Delta Math just doesn't do that. It rounds. So it's 0.378. So if you can't get an intersection, what should you do? Put it in, the calculator is rectangular. It's kind of a trick. Click on the intersection and you can get it as a decimal. Okay, so that's like the workaround. I forgot what it was at this point. Was it 378? Is that what it was? Okay.